Welcome to another session whereby we are going to look at pressure in liquids. And to start with, we want to look at the factors affecting pressure in liquids. And remember, on the onset, we had said that pressure is acting, or pressure acts on the three states of matter, that's the solids, liquids, and gases. So now we get to the second section whereby we are talking about pressure in liquids. And this first part, we want to see some of the factors affecting pressure in liquids. One of the factors that we look at is the depth of the liquid. That is the, can also give it as the liquid column. Now, when we talk about the depth of the liquid, we know that pressure increases with depth. That is, pressure in liquids increases with depth. And we are going to see this by the virtue of the fact that uh, most of the dams are constructed with thicker walls at the bottom than at the top. This is because pressure is greater at the bottom as compared to the top. So pressure increasing with the depth of liquids explains why a diver at the bottom of the sea experiences more pressure due to more weight of water above him than a diver near the top or the surface of the sea. So from that particular point, we can also look at another factor which is going to help us move on with this topic well. The second factor affecting pressure in liquids, we have density. Now, density, when we talk about density or the density of the liquid, different liquids have different densities. So, depending on the liquid that is in question or that is being used, then it experiences different levels of pressure. So, pressure in liquids increases with the density of the liquid. Of pressure with the variation of pressure with the depth of liquids, we want to consider a tall tin with the holes A, B, and C equally spaced on one side along a vertical line as shown below. When the tin is filled with water, the water jets out of the holes with that from hole A thrown farthest, followed by that from hole B, and lastly from hole C. So this means that pressure of water at A is greater than that pressure at B, and pressure at B is greater than that pressure at C. Hence, pressure in liquids increases with depth. So moving to the next presentation to emphasize more on what we are having. This is a diagram, a picture of a liquid in a container, and you can see those jets as we have seen in the diagram above. So check that video. Water is being put into a container and you can see those jets. The jet at the lowest level is the farthest, followed by the one above it. The jet at the highest point has the least jet. The jet is not moving that far. So you can check on that video. It explains this pressure in liquids in relation to the depth very well. Back, we have some images here showing how walls are thickened at the bottom due to the high pressure exerted by water in a dam. So these are the uppermost level. We have thin walls. Then as you move down or deeper, we have thick walls because of the high pressure being exerted. Then this is also another diagram here to show the thick walls at the bottom in a dam. That one is a very good illustration there to show concept of dams. Then we want to demonstrate that pressure at equal depth acts equally in all directions. So in this case, we consider a tin with two similar holes on each side at same height as shown alongside. When the tin is filled with water, it is observed that water travels out of the holes equal horizontal distance from the jet, so or from the can. Therefore, pressure exerted at equal depth is same in all directions. This is what is shown here. You can see this can containing water. There are these two holes at the same level, horizontal level. Then when water is filled here, the two holes throw jets equal distances from the can, as you can see. Therefore, pressure exerted at equal depth is same in all directions. Then we want now to look at the fluid pressure formula. This is the formula to determine pressure in liquids. So under this part, first of all, we want to consider a container with cross-section area A, which is filled with a liquid of density rho to the height h as shown. So you can see this diagram here. The height is here h, cross-section area of the container is A. This is the liquid. Then what we have next? From that part now, we can determine pressure P exerted at the bottom base of the column of the container by the weight of the liquid above it has given. Now, from the definition, we know that pressure is equal to force over area, and force is a weight. And in this case, we are looking at the weight of the liquid. So how do we find the weight of the liquid? In this case, we have the cross-section area and we have the height. So that one is going to help us determine the volume. Now, once we have the volume of this liquid, we multiply by the density. Volume times density gives us mass. And from what we have learned in the topic force, for us to get weight from mass is mass times gravity. So volume times density times g will give us weight. So we substitute in this formula pressure is equal to force over area, where now we have AH rho g over A, whereby we said over area. So this area and area will cancel out. Then we have pressure in liquids is equal to height times density times G. Now this is the fluid pressure formula. From the formula, it's clear that pressure in fluids does not depend on cross-section area of the container holding the liquid. So moving to the first example under that part, we can say a diver working underwater is 15 meters below the surface of the sea. Calculate the pressure due water experienced by the diver, and we are supposed to take our G to be 10 newtons per kilogram and the density of seawater to be equal to 1.03 grams per cubic centimeters. Now, we've already said that pressure does not depend on the shape of the cross-section area of the container. That means that we are going to use the formula pressure is equal to height times density of the liquid times the G, gravity. So in this case, we have height is 15 meters. So all of them must be in SI units. The height is 15 meters, that is the unit, SI unit for length, meters, times the density has been given in grams per cubic centimeters. So we have to change that to kilogram per cubic meter. So we multiply by 1000. We have 1030 kilograms per cubic meter. Then times G. So you can see now we have this G here, 10 newtons per kilogram. That gives us 154,500 newtons per cubic per square meter. 154,500 newtons per square meter. Now that is the pressure exerted by on the diver by the water column. So next we have another question here. The figure below shows a liquid in a pail So the liquid height is 45 centimeters in that pail. If the liquid has a density of 0.79 grams per cubic centimeters, we are supposed to determine the pressure exerted at the bottom of the pail by the liquid. Pressure exerted at the bottom of the pail by the liquid. Again, the formula for this is pressure is equal to height times density times G. Still, the height here we have 45 centimeters. Convert that one into meters, which is the SI unit of length. So it is 45 over 100 to give us 0.45 meters times the density given is given in grams per cubic centimeters. We convert that to the SI unit of density, which is kilogram per cubic meter. So times 1000, we are going to get 790 kilograms per cubic meter times G, which is 10 newtons per kilogram. So in that case, when we multiply this, we are going to get 3555 newtons per square meter. Very lovely, very simple questions. Once you get the concept of the formula, you are able to solve. Moving to the next one, we have a question from that part that we are supposed to suggest a reason why pail manufacturers prefer the shape shown to other shapes. There is that shape which has been given there, this shape here. Why do manufacturers prefer this shape? So we are giving a reason that this is to reduce the height of the pail but maintain the capacity. This reduces the pressure exerted by the liquid at the bottom of the pail. So that's a very good question there. Then we have another question here. More questions. We calculate the pressure exerted by 76 millimeters column of mercury, given that its density is 13.6 grams per cubic centimeters. As usual, mercury is a liquid, that is pressure of liquids exerted by liquids. So in this case, we are again saying pressure is equal to height times density times G. So the first step, we convert all these measurements to this SI unit form. In that case, we are going to have 76 millimeters converted to meters. We divide by 1000. So in that case, we get 0.76 meters. Then times the density, which is given in as 13.6 grams per cubic centimeters. We'll have times 1000, it will be 13,600 kilograms per cubic meter times 10 newtons per kilogram. I think this one, let's use 76 over 1000 so that we can maintain that conversion in a correct way. 76 over 1000. So once you work it out here, I think this value is should be 0.076. So we are going to get 103,360 newtons per square meters. Very simple calculations once you got the concept of the formula. So to that point, we want to call it a lesson for pressure in liquids, and I believe most of the concepts have been highlighted well. And giving it a recap, we can ask a student to state two factors affecting pressure in liquids, and we expect a student to state the first point as the density of the liquid, then the second one the liquid column or the depth of the liquid. Then moving further, you've seen why we have the dams have thicker walls at the bottom as compared to at the top. That is because of pressure differences. At the bottom, we have more or a higher pressure being exerted. Therefore, avoiding destruction, we construct or we make thicker walls at the bottom. Then you've seen the fluid pressure formula, whereby we've derived and we have had pressure is equal to the height times the density of the liquid times G. And we have used that formula in doing our calculations. Thank you for your time. That is the end of our lesson. Thank you.